Hello, everyone, and welcome to this webinar hosted by the Reinforce project. My name is Chris Lintott. I'm an astronomer at the University of Oxford, where I run the Zooniverse Citizen Science Project. And it's my job this afternoon to get out and allow our lineup of speakers drawn project to tell you about what they've been doing on the topic of helping scientists in the gravitational wave noise hunt. Reinforce stands for Research Infrastructures for Citizens in Europe. It's a collection of educators, academics, researchers, and scientists who have come together to try and build new and novel projects that help volunteers participate fully in. So we're joined to learn about this. Reinforce is part of a growing number of citizen science projects which have this aim of public participation in science. For me, the journey with science started, well, probably when I was a small child with a small telescope trying to discover supernovae and comets. Recently, in 2011, when the group here in Oxford launched the Galaxy project, and were overwhelmed by and then hundreds of people who visit our site, contribute classifications of galaxies. This was something of a surprise to us as astronomers. We hadn't really anticipated either the level of it that we'd get from the public, nor how capable these citizen scientists would be. They went on to make not only many classifications that we could use, but many exciting discoveries of the unexpected in the data, something that's become a key of the citizen science methodology. And so after that project, we decided that as experimental scientists, we wanted to understand why these participated. And though we eventually did some questionnaires and some proper social science research, we created a set of natural experiments by building new projects within what became the Zooniverse. And it became to try projects that we might not. So we tested the capabilities and interests of citizen scientists. And I have a very long track record now, more than a decade, of predicting that various projects won't, only to find that they do. One of the first was the Planet Hunters project. People data from NASA's Kepler Space Telescope, which looks at planets around other stars. More recently, NASA's TESS satellite. So this is a project that involves looking not at nice images of galaxies or pictures of animals or anything like that, but rather it involves looking at graphs. So we weren't sure that anyone would do this, but people dived in, and more than 100 planets now being discovered by citizen scientists. On top of that, we built called Gravity, which used data from LIGO for glitches, for noise in gravitational data. And to my great surprise, tens of thousands of people have taken part in that project. And for me, that's the inspiration for much of what we're trying to do at Reinforce. This idea that people are willing to quite abstract data, spend time with it to try and understand the universe contribution to science. Explore all sorts of aspects of that behavior and discussion this afternoon. While listening to my colleagues, feel free to ask questions. And there is a Q&A feature on the webinar software on Zoom. Please use Q&A if you can. If you put something in chat, one of my colleagues may rescue it, but you can use the Q&A. We have a little bit of time between the talk, but we've also side time an hour to go through the Q&A in detail. So I'm looking forward to your questions. And with that, hand over to the first speaker. So our first speaker is Stavros Katsanetzis, who's the project coordinator at the European Gravitational Observatory. Stavros, over to you.
Thank you very much, Chris. Let me share my screen. Yes, probably I can, I don't know if I can, yeah. Is it visible to all? I mean, let me see. Is it? Is it visible to all?
Yes, that's working for us.
Huh? Is
Yeah,
it
that's
okay?
fine.
Yeah,
Yes.
okay. So I will very shortly talk because we talk about gravitational waves. That is not the only large infrastructure that it is concerned. We have four, let's say, thematics and four large infrastructures: Virgo, that you hear about, the Kilometer Cube, an observatory at the bottom of the Mediterranean Sea, LHC at CERN, that you all know, and also the cosmic rays. Now, let me say a few things about the goals of this. It's a quite particular citizen science project because there is a large component that it shows the embedding of these large infrastructures in the environment. You will see that we try, as I say very often, we try to understand, before you understand the cosmos, the universe as cosmos, you have first to understand the environment, the earth, the atmosphere, even society, if you wish, as an environment, because it can produce noise, whichever way we see it, we'll talk about it. Then you have a second big goal is that since a few years now, 20, 30 years now, we have moved from only light or electromagnetic waves as a messenger from the universe. We have gone to other messengers, and these are gravitational waves, neutrinos, and cosmic rays, for instance, in our case. And we'll be talking to that. So we're going beyond the visual in some sense. And also, if you start going beyond the visual, then you start thinking about how more senses at one, not only the vision, but also the hearing, the sound, can help you understand the universe. So you can use it also as, let's say, an epistemological way to multiply the ways you apprehend, say in French, to understand the universe, but at the same time, it can help inclusion. I have access by people that, for instance, are blind, not seeing. Then all this, since it will be science and it will be participative science, it helps critical thinking, and we all know, and I will not go into details, we need critical thinking in the world of digital connectivity we're living, with all the things political that's happening. And then one of the things we, at least in science, we believe we know how to do is how you separate signal from background noise, to formulate hypotheses, to estimate your own biases, not to be sure what you're doing unless you really have tested it properly, manage the uncertainty in some way, and of course, try to promote collective thinking against herd thinking. Last but not least, we are also experimenting how ways of transversing traditional frontiers of the modes of apprehension of reality, for instance, art and science project. So an example, you will hear more about it later, so we'll go very fast here. You have gravitational waves, deformations of space-time. What you have to do is you have to try to see how two masses in free fall, as you would say in our gravitational jargon, change their distance by 1,000th of the diameter of the proton, 10 to the minus 18 meters, that they are distant in 1 kilometer. So you can see how difficult it is first, and of course you immediately can understand that then you have to separate this from what happens all around it, all the influences of the environment, understand the environment. Furthermore, the frequencies of deformation of light, because it is an interferometer, it's not sound itself, but it is light that you detect through light. It happens that the frequency of deformation are between 20 hertz and 20 kilohertz. So it explains why we say that we are hearing the universe. So we introduce the sound in some way already naturally through that. And of course, all this led in the first discovery by LIGO and then also the colleagues of Virgo, and then Virgo came a little bit later, but still now we cannot operate, but all three in a global network, seeing essentially one violent event every week when we are operating. So I said it already, if you want to understand the universe, you have to understand many other things. The impact that it can have in your detector, the sea waves, seismic noise, radio waves, electromagnetic waves, helicopters, planes, trucks that are passing by, anthropogenic noise, atmospheric, the passage of the clouds, and even cosmic rays. So this makes that we have a lot of collaborations, both local and international, with geoscientists, ecologists, atmospheric scientists, regional instance anthropogenic noises. And this is a taint. This is tainting what we will propose. We propose in the citizen science program. I will not go through what we are actually proposing gravitational waves because you'll hear it in more detail later. Then you have to think that what I just said, we understand now the universe not only as light and electromagnetics, but also multi-messenger, and therefore we added to the electromagnetic, the gravitational wave, the cosmic rays and neutrinos. And if I take the neutrinos, you see, again, we try to see neutrinos at the bottom of the sea through their light, but also some sound. We can try to hear the very high energy neutrinos through their acoustic impact. And then, of course, then life itself, for instance, bioluminescent organisms or dolphins can give optical signals or acoustic signals, dolphin and whales and all that. So at the same time that you study the cosmos, you're studying the life in the deep that, as we know, it makes a big part of the biosphere, and it is deeply unknown. We don't know very well how it happens. And they have, for instance, 15 years of data that would be available for citizen science to study and understand. And I mean, this is publicity if you wish for the next webinar that we will be talking about. And then again, cosmic rays, you can use the cosmic rays, the muons, for instance, as a radiography technique. So you can use the fact that transverse structures to understand volcanoes, to search for instance, you look in tumulus and to look for anthropic structures internally inside the tumulus, which is a worldwide way of everybody was having tumuli in the antiquity for the dead and things like that. So it can be an archaeological thing, and of course industrial control. And cosmic rays, I don't have here a slide for that, can be also a climate index by distributing to schools and have the people themselves controlling the climate change, among other things. Last but not least, you also can get through the physics at LHC, you can look things that you cannot all the time do through algorithms. Try to see, for instance, off-center vertices, which would mean, let's say, new physics. It can be dark matter, it can be Higgses that are doing strange things. So again, there you go a little bit away from the environment, but still not very far from looking at something that, of course, there you are more on the biological style. This can have certainly biological impacts. So this is one of the things we're doing. Then the second, we're happy we are collaborating, of course, with the previous speaker and Chris and the University of Oxford, because now we have a common platform, Zoo Universe, that has 1 million volunteers. That case is very interesting and very common. And then we're developing all together what I just said, again, you will be hearing about that, new sonification software, where we can try all the signals to translate them in sound, and so that we increase inclusiveness, but also increase, as I said, the epistemological reach of what we're doing. So, as I said, common platform, you will have very soon 4 demonstrators, about kilometer cube for gravitational waves, for LHC, and for cosmic rays inside the Zoo Universe. And also, as I said, again, we'll hear about it. We have sound sonification of all this due to our collaboration with Wanda, Mercedes Diaz and Beatriz Garcia and other people working with them in the US and in Argentina. And I think that's a great asset of what we're doing. It will be the biggest, I think, innovation we will be doing. And this is not all. Last but not least, we are also very active in 2 other domains. One is critical thinking. We are having a connection we are having a connection with Saul Perlmutter in Berkeley and his sense and sensibility in science, where it is again a program where you try to develop critical thinking. I talked about it in the beginning. And also we prepared, and we will hope we will have some more art and science projects. For instance, we made this exhibition called The Rhythm of Space, and where I have here a poem in Italian where you had people going towards Alzheimer, not yet arriving there, but when they saw the black holes and all that, they felt they had the affective sensing of a black hole as loss of information. It is a magnificent poem in Italian. I'll let you read it afterwards in the slides. So, in conclusion, I said it all, and I tried to make a sort of scheme that includes what we call the full cosmos, where cosmos here denotes, as in antiquity, both the universe, Earth, society, and the human. Therefore, the multi-messenger aspect, the geoscientific, atmospheric, biological aspect of the environment, the societal impact, the anthropogenic impact, the critical thinking, and the human, where we try to increase the possibilities of the human through multisensorial apprehension, art and science, and of course, inclusion. So I think that's all I wanted to say, and thank you very much for listening.
Well, thank you, Stavros, for an excellent introduction to the project. Whenever you talk about the cosmos in that way, I always think that the astronomical bit, the universe, is the simplest part of it, which is slightly humbling for an astronomer. But let's hear more now about the most advanced of the demonstrators so far, which is the Gravitational Wave Noise Hunting Demonstrator, which I know lots of you are here to hear about. And to introduce us to that, we're going to hear from Massimiliano Rosano from the University of Pisa, who's leading the reinforced work on that topic. So if you want to go ahead, Massimiliano, and share your screen, it's over to you.
Yes, can you hear me?
We can, yeah.
Yes, yes.
Good. Okay. Here we go. Okay, good afternoon, everyone. So today I'd like to talk about the effort that we are putting together in order to prepare this demonstrator about gravitational wave noise hunting. And we hope that thanks to this demonstrator, you all will soon be involved in our search for gravitational waves. And this is, of course, a work that is being done within a group, a work package. So this is on behalf of all the people that are working on that. So first of all, let's start with something that happened a long time ago in a galaxy far, far away, which are two black holes that are shaking the space-time while they are spiraling one into each other, and eventually they will emerge and they will build a new black hole. And this black hole will start ringing and shaking the space-time. And this shaking of the space-time we call gravitational waves. So actually, it's very interesting because the gravitational waves just open a totally new windows on the universe. So thanks to gravitational wave, we can study the gravitational field, we can study the distribution of masses, we can probe everything that is dark, which is black holes, but also other astrophysical sources that are not emitting light. But we can also test the laws of general relativity and the laws of gravity, because we have the general relativity, which is our best theory about gravity, but this is maybe this is not the final theory. So eventually, thanks to gravitational wave, we will be also able to eventually find something different. And of course, we also would like to investigate the cosmology. So go back to thanks to the primordial gravitational waves, go back very close to the Big Bang. And thanks to gravitational waves, we can open also a new window in the cosmos, in the sense that, as Stavros just said, we can do what we call the multi-messenger astrophysics, because traditional astronomy was based on light, but now we can detect gravitational waves, we can detect neutrinos, and all these cosmic messengers can carry complementary information. And that's why we are so interested in that. And here you can find a quick timeline about gravitational waves. Later on, there will be a talk focused on Virgo and on the gravitational wave detectors. Just to put things in context, as you probably know, in 1915, Einstein put together his general relativity, which is this new theory of gravity. And after 1 year, he was able to predict the existence of gravitational waves coming out from this equation of general relativity. And then it was a set of attempts in order to detect this tiny, very tiny fluctuation in space-time. And there are some first detection using some first detectors during the 60s. And later on in the 70s and the 80s, we are coming in a new era that is based on the actual detectors, which are based on interferometry. We call these interferometers. And here in Italy, we have, in Europe, we have Virgo, which is very close to Pisa, that was initially studied by this group of Italian and French scientists. In Italy, it was Alberto Giazzotto. And meanwhile, in the US, there was the LIGO project coming on. So these detectors come together, they start observing, and eventually, after a period of observation where basically no gravitational waves were detected, the scientists decided to go and aiming a tenfold increase in sensitivity. And these led to what we call the advanced detectors, so advanced Virgo and advanced LIGO. And in 2015, finally, we had the first detection of a binary black hole gravitational waves. Later on, we have other observing run, which are the way that we call our observing period. And the last one was in ending this year. This is the third observing run that we call O3. And we have detected several tens of these events. And what are the sources of these gravitational waves? Well, we know that these are ripples in space-time. We know that they travel at the speed of light. And we know that there are violent phenomena that are creating these waves. So we can think about what we call the coalescence of compact binary systems, which means two black holes, two neutron stars, or black hole and neutron star that are in spiraling and coming together, and eventually they merge. But can be anything else. It can be supernova explosions, can be something that we don't know yet. And there is also, we expect to have also a set of continuous emission coming from rotating neutron stars, what we call pulsars, or from a background, a stochastic background of continuous waves, and again, others, which is the unexpected. So these gravitational waves are producing very tiny signals. And when I say very tiny, I mean 10 to the minus 18 meters. So it's a very tiny measure. So that's why we devise these laser interferometers like Virgo. Later on, Julia will talk more in details about how these things are working. But this is very important because these led to the scope of the demonstrator, because during this project, we will help the citizen scientists to collaborate and to help us to understand the noise in these gravitational wave detectors. And this is very important because exactly as it happens with our ear, we have a sensitivity that depends on the frequency. And also this is the same situation with Virgo, with the gravitational wave detectors. We have different sources of what we call noise, which calls background noise. This could come from thermal processes, this could come from quantum mechanics, this could come from seismic motion, etc. And what we want to do is to be able to understand this noise so that we can lower it, and in this way we can get more science and we can be more and more sensitive. So among these different sources noises, there are some transient events coming from noise that we call glitches. That's because the instrument is not perfectly stationary, because everything around the instrument will happen, like environmental noise, atmospheric turbulence, etc. So these could induce a different source of noises, including these glitches. And if you are able to detect these glitches and to classify and to characterize them, eventually you will be able to find the origin of these glitches and eventually to remove them. And unfortunately, these are quite complex. They have a complex morphology. So if you look at these plots at the bottom, you can see the time frequency evolution. This is what we call the time frequency evolution. And you can see that two different set of glitches, they might have different ways. So if you will collaborate with us, you will also get the chance to give funny names to these glitches. So one, we call it blip. The other one, I decided this name, Elaine Falcon, but this clearly, we have other names for this as well. And on the right, you can see exactly this big yellow triangle that is almost covering the tiny signal here, that is the gravitational waves. And here you have this very big glitch. So you want to be able to get rid of these glitches. So how we do this? Well, actually, the idea is that we have a machine learning algorithm that is able to classify these glitches, but we have a huge amount of glitches. We have a few glitches per second in some cases. So we need to have an input in order to train our machine learning models. And that's where the citizen scientists came into play. This is very important because how you can help? Well, you can look at our data, you can look at glitches, and you can look at also at other noise sources, not just glitches, and you can help to characterize this. There is also already a citizen science project, which is called Gravity Spy, that was put together by our colleagues in LIGO. And the idea is exactly the same that is depicted here. So how does machine learning work? Well, you give more and more example of glitches. Like here, you can see more and more example of animals, duck, duck, and not duck. And after a period of training, the algorithms is able to look at new images and decide whether this is a duck or this is not a duck, or in our case, this is a glitch. What kind of glitch? Or maybe this is not a glitch, it is a real signal. And that's why it's very important. So how you can contribute? Well, you can contribute to noise identification, noise hunting, and noise classification. So we have put together a demonstrator, and now I will give you a very tiny example of how this demonstrator is coming into play. Also, because in this way, you are able to understand what you'll be asked to do when this demonstrator will come online. And of course, it's very important, it's very nice to share the findings and to find the new features, because we know that there is a certain amount of glitch, but there are other glitches that we haven't yet classified. So among this data, it might be happening that you will be able to find some new noise, some new glitch types, and new noise sources, and the citizens will help clearly into unveiling these new rare glitches. And as you have seen already, but you will see now, this data initially will be presented as an images, but also we plan to add the sounds, and this is something that also goes into the direction of the sonification that Stavros just mentioned. So, and how these things look like? Well, on the left, you can see this very huge panel where you can see this very complex image, where you can basically see at different time how the profile in frequency and how the energy of the noise is concentrated. This is what we call the spectrum, so the energy distribution. And you can see that on this rectangle, this box on the right, you can see an example of a glitch. So the road ahead. So far in our work package, what we have done, the first steps were clearly focused on the data. So select the data, create a specific formats for the data using LIGO and Virgo data. And we have done this already. So we have a first initial sample of data. Clearly from these data sets, we have created some visuals, some images, some sounds, etc. So the next step will be that the steps that we are working now, it's develop the machine learning algorithms, and also developing and deploy the website and the portal on the Zoo Universe. So we have a prototype that I'm going to show you. We have tested some first examples of a workflow of tasks that citizens will be able to do. And eventually, we hope that in the next months, we will be able to launch the website. And after that, we will do some comparative analysis, comparing humans and machine learning and stuff. So let's go on the demonstrator side. This is what we have done so far. Let me see if I can open the website. So you should be able to look at this this demonstrator. This is the one that also Stavros was saying before. So these are just some examples. So initially you will be presented with something like that, like, okay, what is this? How many glitches do you see in this image? Well, let's say I can see 1 or 2 glitch, let's say 1. And then you're asked to draw a rectangle around them, because like here, for instance, and you can say, oh, what kind of glitch do you think it is? So there are class 1, class 2, there will be, of course, the actual names, none of the above. Maybe this is something that we never seen. So let's do none of the above, and that's it. And after that, you can get more and more and more. Let's say you see here, I don't know, 1, and stuff like that. So, and then you get something like this, which is interesting because this is a single one. This is a repetition of more than 1 glitches. Let's say 3 or more, or let's say just 3. And then you can go here and say, okay, this one, class 1, I'm happy with this. Then there's another, which is, let's say this one. All right, still class 1, I'm happy with this. And then like this, or something like that. And so we have identified 3 class 1. So you will be asked also to not just to say, okay, this is a glitch of this class, but also to say where they are. Okay, and so on. So this is one example of a task. Of course, we have other, the study of the noise is a quite complex task. So we have other ideas. We are testing different tasks, but this is just an idea of what you will be able to do. And let's go back to the conclusion. So we are very happy to start very soon with this project, and we hope that pretty soon we will be able to. Oops, sorry. Here we go. We will be able to reach the moment where the demonstrator will be online. Just remember that if we have less noise, this means that we are more sensitive. If we are more sensitive, we can see more gravitational wave events, and this means more science. So just stay tuned because we will be ready for lunch very soon. Thank you very much.
Thank you very much. It's always great to see somebody doing a live demo on a webinar. So well done for being brave. It was great to see that in action. I can see we've got our first question has appeared. Do use the question and answer function on Zoom if you want to ask a question, and we'll take them at the end because we're already running slightly behind time. So let me hand over now to a colleague, Beatrice Garcia, who's going to talk about one of the most exciting parts of the Reinforce project for me, which is our attempt to use sonification to make data more accessible and to explore in new ways. Professor Garcia is from the National Technological University and many other places, as a past president of the International Astronomical Union Commission for Education. So Beatrice, please take it away.
Thank you very much. Can you hear me and see the screen?
We can hear you. Yeah, that's fine.
Okay, thank you very much. Well, this talk is about one of the packages in Reinforce. We are giving our greetings from the far side. We live in Argentina. And this working package in particular is devoted to work with the access to the astronomical and scientific performance with the aim to give opportunity for multiple learning. As you know, as my colleagues just mentioned, the astronomy in general is a science devoted to the people who can see, but anyone can develop this ability. And of course, there are many scientists and citizens who cannot see. Look at this beautiful Milky Way at the right, top right, but also look below, look at the bottom, this very happy guy touching the sky, touching the stars with the hands, because the access to the knowledge, the access to the nature can be made through one or more senses. For example, Look now, the galaxy, the right galaxy is a very famous one, it's a Whirlpool galaxy. And now look at the same galaxy in different wavelengths, under different eyes, with different instruments. Because almost all that we know about the universe arrives from energies that the eyes cannot see. So the astrophysics multi-wavelength and recently the astrophysics multi-messenger open a new windows to the cosmos. So in the same way, we can access the information with more than one sense. The participation in this regular stream of performance has not been taken into account from the beginning in the development of the development agenda. It means not always we are thinking in the people who cannot have the same approach to the nature to permit these people the development, the personal, the human development, but also the scientific one. It appears that the international efforts in general has been limited to the packages that address big data visualization, and remember that big data drives all-inclusive aspects of social and human development. Here you can see one that Diaz Merced, Stavros mentioned here, is our mentor, is a blind astronomer. There are many blind astronomers, and we follow her way to try to permit the access to the information all the people. We made a preliminary study on the software, the available softwares devoted to sonify the larger data sets and symmetrically display the plots. And the problem with the available sonification tools is that they are not accessible according to the international standards. So the idea of this proposal as part of Reinforce is try to develop a user-centered approach to permit the data analysis and data retrieval, because it's not enough the data analysis, and give the people with other sensory styles the possibility to explore the scientific data and make science. Of course, this kind of work is not made by only one person. Here are many of our collaborators, because the project integrates multidisciplinary and interdisciplinary astronomers, engineers, software designers, educators, sociologists, both able and disabled. Which were our first consideration for this new design? Well, we need to access the scientific data. We want to access the scientific data, not only for thinking in data from Earth, but also with instruments on board of satellites. And of course, we have the databases. In this sense, the proposal is to create a human-computer interface which permit the access, but also the collection, the sonification, and the final analysis of astrophysical data. We need to test the efficiency of this kind of tool and also the effectiveness of the research in different cultural settings, cultural environments. And for that, probably the most important thing is to develop a paradigm for training researchers and interested citizen scientists to start using new technique. For that, I know this is not very simple. We need to change our mind to do that. The software we are developing in the framework of Reinforce has many main characteristics. One is the use of the sound as a complement of visualization. We need to replace the visualization if we are blind, but if we can see, we will access in a multimodal way to the data. The design is a user-centered one. This means that the user is the most important character in this play. We need to combine the features with the necessary and scientific efficiency, but also according the needs of the user. The software is completely open source and cross-platform, and in this sense, all the people all over the world will be access to the software to use it in the way that they want. This tool aims to eliminate the barriers presented by current technology for the people with sensory and motor disabilities, and allows to improve the work with different styles of data exploration, even if you are a scientist. This is a very, very simple scheme about what we have as input and output of the software and the tool. And you can see, you can enter a table, a 2 columns Excel file, or you can enter sound, or you can enter even the complex data from Ego Observatory. You will display, you will have a display with a plot, a sound. You can mark the data. You can define a grid. You can apply mathematical functions. And finally, you can save all the things that you are working on. Here is this description, this scheme implies a modular design, as you can see here in this slide. There is a core, it's a nucleus of the software, but you have different packages on which you can act and modify according the sensitivity of the user or the needs of the user. Here in the display that you can see, this is the screen of the software. You have a section to open and import data, to save or export data. You have a graphic section, a mathematical functions window, and the sound functionalities, all in the same window. This perhaps is not very important for everybody, but for the blind people, the pop-ups are a real problem. You need to have all the information on the same screen. The other thing is the amount of data. Well, Casanueva allows the input of large data sets, and Ego data sets are really large. Perhaps millions of data. You need to deploy this data quickly and analyze it. Probably the most important thing for this software is the summarization. The sound synthesis model is a very important topic in this development, because the main problem with the others, the tools, is that the manipulation and the acting and altering the sound at will is not possible. So in this case, you will act on the data in the way that you want and you need. Well, I cannot hear the sound here, but you can see 3 volunteers, because as this is a user-centered software, you need the volunteers, and you need to make a particular study called the focus group study. You need to have the feedback all the time. And for this reason, the development is not so fast. It's with a lot of stops to correct problems and things not very, very well developed for the blind or other kind of ways to access the sound. But it's interesting to see, for example, here at the end, the last volunteer, Emma, that she said that I have more confidence and freedom as well, and I felt like I was a lot more able to access the data that I want to do, and also that her thought to do. I know here is a problem. I need to change my machine. I know that you will experience some noise. Sorry for that. But I want to show you the Sono in action. Please let me know if you hear something. You are here probably the voiceover. This is a kind in the blind people access to the computer. All the time is on. You can recover the data, deploy the data. This is part of the noise shown by Massimiliano a few seconds ago. And here you are mapping in frequency the noise sound. This is the noise of the data from ego. What about the future? Well, we expect to everybody adopt the technique, because the technique, we believe, is a good start, a good window to open to the universe. And we are sure that this kind of approach will force the nations to carry out honest assessment about the gap between the report as achieved and the quality of participation of the disabled. Is not the same. There is a gap. We need to systematize a report format where national science organizations put in evidence that the developments are user-centered designed. Also, we need a better recognition about the multisensorial exploration as a valid study of the data, and of course, stimulate the funding agencies to ensure that the proposals include people with disabilities and diversities. And the benefits, well, the benefits are a lot. There are very, very clear evidence that this kind of approach, in the same sense that the multi-wavelength approach, this approach, the multimodal approach, increase the ability to identify features, signatures in the information, bring the people with disabilities to the field. The most part of the scientists with disabilities have a lot of problems to make science. Increase the amount of scientific discoveries for blind, are not blind researchers. And one of our main goals are to enhance the work of the scientists, accepting this different way of data exploration, different styles, more perspectives, and more experience. Because we live in a very, very interesting moment, in a very, very interesting time to mainstream those that historically have been completely left out of the research, and of course increasing the enterprising spirit. This approach will motivate, without any doubt, a most humanistic metric and model of competition that will generate more inclusiveness. Remember the United Nations Human Development Report of 2015, which says a critical human deprivation is not use, misuse, or underuse the deep human potential for human development enhancing work. And finally, look at this image. I love this image. These are three moments or three possibilities, and we can choose this. We normally are working and work and we talk about equality. This is the image to the left. Equality is to give everyone the tools. For example, a computer. Or for example, the possibility to go and see a match. This is a baseball match. Well, I didn't find a football match, but it's the same. What is equity? Equity is assure that all the people can see the match. But that is not enough. You need to address the causes of inequity, and in this way, you will remove the systemic barriers, which is the right image. So thank you very much. And I hope this new kind to access the information open as the multi-wavelength and multi-messenger, a new way to access the cosmos, a multi-modal approach. Thank you very much.
Wonderful stuff. Thank you. I think it's a really important part of the work, and it's great to have it amongst our talks today. So thank you, those of you who've asked questions. Keep asking questions on the Q&A. We'll answer as we go and at the end. But I'm going to move straight on now to our next speaker. Our next speaker is Julia Casanueva, who will be talking about Virgo and the International Gravitational Wave Network. Julia is a researcher at the Interferometer Sensing and Control Group at EGO. So please take it away.
Thank you. I will start sharing my screen. Okay, so good afternoon. I will speak about Virgo and how gravitational wave detectors are able to actually detect gravitational waves. I will try to give an overview of the international network of detectors. So whenever we want to design a detector, the first question we need to ask ourselves is, what do we want to measure? So as Massimiliano said before, gravitational waves are ripples, perturbation of the space-time. But this still sounds a bit abstract. So, so we need to ask ourselves, what's the effect when a gravitational wave crosses the Earth? So if you have two objects, two masses in free-falling masses, the effect of a gravitational wave would be that the distance between them would change. In particular, we would find that the distance will increase in one direction and it will decrease in the perpendicular one. So the effect would be differential. However, we cannot think about any instrument, measurement instrument usual, classical, like you cannot think about something physical to measure distance, because it will itself get distorted by this gravitational wave. So we needed to change tactics. And the idea was to use, to measure time instead of distance. So we choose light because we understand very well light. And we measure the time that takes light to travel this distance we want to measure. So if it takes more time, this means the distance will be longer. And if it takes shorter time, the distance would be shorter as well. So together with these two information, so we are going to use light to measure time, to measure distance, and the effect is differential. It came up that the ideal instrument would be a Michelson interferometer. So this is what we see here in the slide. Basically, we have a light source, a laser beam, that will be sent to a beam splitter that would split the beam in two identical beams. And each one of them would be sent to travel a completely different path. And at the end of the path, there would be placed a mirror that would oblige light to come back. So these two beams would have traveled two completely different paths. And the mirror obliged them to come back and re-interfere at the beam splitter. And we can actually monitor how do they interfere if we place a photodetector. So basically what this Michelson interferometer, we like it because this interference pattern would depend on the distance, the path traveled by each one of the beams. So we are basically sensitive to the difference in the distance that both beams have traveled, which is exactly what we want to monitor to detect gravitational waves. So let me say 2 words about this interference, right? So if we have two identical arms of our interferometer, so the length is the same, when they interfere, these two beams, we find something like it is shown here. So the two waves are in opposite phase. So whenever they when they interfere, the maximum of one would correspond perfectly to the minimum of the other one. So the sum would be, they could completely cancel each other and the sum would be 0. And in this condition, we are in what we call dark fringe. If by any chance, for example, a gravitational wave passes and one of the arms become longer than the other, then when they find each other, these two beams, they are not anymore exactly in opposite phase. And when they sum each other, their maximum and the minimum, they won't match again. And so the sum won't be 0, but would be something different. And if we are looking at our photodetector, then we won't see any more dark fringe, but we would get some light. And then we would have known that something has disturbed our detector. So this is the basic principle. But we know that gravitational waves are very small perturbations. So in practice, we need to measure changes of the order of 10 to the minus 18 meters, which is extremely small. So we would have been obliged to build detectors that are like 1,000 kilometers long and to have laser sources of several hundreds of watts, which is very hard. It's impossible to build, actually. So we had to find another way to boost the sensitivity of our detectors and make our interferometer be able to detect such small perturbations. So we came up with the idea of using optical cavities. So we place 2 semi-reflective mirrors in the path of this of the arms, so that when the light comes back, it is obliged to go back and forth each one of the arms many times. In particular, in Virgo right now, we oblige them to go back and forth 300 times. So our arms that initially are quite long already, so they are 3 kilometers long, they are obliged to make 3 kilometers, travel 3 kilometers 300 times, which almost pushed our length to 1,000 kilometers without, with only placing 2 mirrors. And we made the same trick with the input power. In order to increase the input power, as we are working in dark fringe, all the light comes back towards the laser and it's, let's say, lost. So we placed another semi-reflective mirror here so that we can resend back this power that otherwise would be lost. And so we boost our input power by a factor 40. And this way we are able to be as sensitive as to measure such small perturbation as the ones caused by gravitational waves. And this is right now the, let's say, the optical scheme of all the gravitational wave detectors. But of course, the tricky part is that as we are very sensitive, unfortunately, this means that we are sensitive to everything, not only the signal we are interested in, but basically everything becomes a noise source that limit our measurements. So we had to develop extreme techniques to mitigate all the noise sources. So I gather here some of the most relevant examples. So seismic noise is one of the most dangerous noises, and it limits at low frequencies. And so we had to suspend all the optics, all the core optics of our interferometer by super attenuator, which is 9 meters tall. And we managed to get an attenuation of 12 orders of magnitude thanks to them. Also, pressure fluctuations would perturb our laser beam. So we have to work under ultra high vacuum. We have the highest volume of vacuum in Europe at Virgo. Also, our laser source needs to be extremely stable and extremely clean. Our mirrors have to be quite almost perfect, so very polished, very perfect surface without defects. The coatings, which are the covering that makes a piece of glass to become a mirror, they need to be also very, very perfect. The fibers that are used to suspend our mirrors, which are 40 kilos heavy, they also need to be very, very perfect. They are like 400 microns diameter, so it's like 4 hairs put together to suspend a 40 kilos mass. And also, of course, our photodetectors, which will be the core of the detector, because that's how we study interference, they have to be low noise so that we can get all the information. So once we have overcome all these technical efforts, we are able to have a detector as sensitive as we wanted. So here we can see a sensitivity curve of Virgo. So that tells us, it gives us information about what's the smallest gravitational wave that we are able to detect. If the gravitational wave is smaller than this curve, then we won't be able to see it because we would be covered by noise. And so our target, once we have ruled out all the other technical noises, is to improve what we call fundamental ones. There are some noises that are intrinsic to the measurement we're trying to do. And the only thing we can hope is to make some fundamental research to lower them, but we know they cannot disappear, which includes, for example, thermal noise, which is connected to the fact that we work at room temperature and the molecules of our mirrors and our fibers, they move. And then shot noise, this is a quantum noise related to light, the uncertainty on the phase of the light, of the laser. So just 2 words on our detector, Virgo detector. So it's located in the countryside of Pisa in Italy. Its construction started in 1997 as a collaboration between France and Italy. And the first scientific data taking was in 2007. And since then, the collaboration has grown a lot. Now we are 7 European countries working for Virgo, almost 300 scientists, and we managed to get the first detection of a gravitational wave in the 14th of August of 2017. And last thing, so I've talked about how gravitational wave detectors work, but as I said, we are almost our measurements are almost covered by noise. So one only detector can't work. We need more. At least we need 2 detectors to make measurements in coincidence so that we know that it's not just noise. And of course, if you want to also get interesting information with some accuracy from the source of the wave, you need at least 3 detectors. And ideally, the more you have, the better you can estimate and you can study the source of the gravitational wave. You can locate and get much more interesting information. So we are going towards an international network of gravitational wave detectors. So right now I've talked about Virgo, which is the one located in Europe, in Italy, but there's 2 detectors in the United States, one in Livingston and one in Hanford. There's another detector which has been built in Japan, and it's right now under commissioning, and it will be ready to take data soon. And there's another one in India, which is right now in the process of construction. And we also have a smaller detector in Germany, which is called GEO. So basically, this is it. This is all I wanted to say. I hope that I clarified a bit better how these amazing gravitational wave detectors work. Thank you.
Thank you very much for that talk, which I know has answered several of the questions which have come up in the chat. We need to keep going, so I'm going to hand over now to Francesca Spagnolo, who's our EU program coordinator at the European Gravitational Observatory, and she's going to focus briefly on EGO itself. So over to you.
Yeah, thanks, Chris. Very briefly. Good afternoon or good morning, depending on where you are. I'm going to introduce you to the EU programs we run at the European Gravitational Observatory, at EGO. So please, next slide. As you may know, EGO is a consortium of the French CNR, the Centre National de la Recherche Scientifique, and the Italian ANFN, l'Istituto Nazionale di Fisica Nucleare, 2 public research bodies. Research is therefore crucial to EGO activities, and as you can see from this slide, we run several EU-funded projects covering different actions: research and innovation, education, exchange of highly qualified personnel, and cooperation in science and technology. From next slide, please. From this diagram, you can see the many activities funded by the EU programs, which include data science, outreach, education and citizen science, environmental studies within 2020. For example, we are building a movable environmental sensor, will be developed for use in Gravitational Waves Observatory. And then we also, last but not least, have programs working on multi-messenger science. Actually, multi-messenger science is covered by all the 3 research and innovation actions funded under the Horizon 2020 program. IGO, as you know, please next slide, is the coordinator of Reinforce, which is funded under the Science Guidance for Society program of Horizon 2020. And it is a true citizen science project aimed at minimizing the knowledge gap between large research infrastructures such as IGO and society through the involvement of 100,000 citizens, including, as already said, senior and visually impaired citizens. But we also, please next slide, we are also partners of other Horizon 2020 projects in the field of physics, such as ESCAPE and AHEAD 2020. Both of these projects, being research and innovation actions, consist of activities aiming to establish new knowledge and involve a large number of European research centers, observatories and infrastructure, such as the Cherenkov Telescope Array, for example, or the well-known CERN. The aim of these projects is to enhance networking and cooperation between scientific communities in different physics domains, including astrophysics and particle physics, of course. But we also, next slide, please. We also collaborate with the university and research center across the EU for education and outreach activities, as in the Cost Action G2Net and in the Erasmus Plus project Frontiers. Particular Frontiers aims at integrating modern physics into the school curriculum and to bring into the classroom the discoveries of the Nobel Prizes winners, while the Cost Action G2Net is an European cooperation in science and technology project, which is coordinated by IGO and is aimed at promoting synergies of techniques drawing from many different disciplines, including physics, mathematics, machine learning, robotics. Finally, we are partner in a Marie Curie Rise Action for the exchange of researchers between Europe, the US and Japan, and we recently won another project for the exchange of researchers, which is due to start next July, depending on the global pandemic, of course. Just for your knowledge, the total EU funded budget for this project is for IGO alone over €1 million to be spent on the recruitment of research personnel, of course, but also on networking activities, education and outreach, including innovative outreach practices, such as, for example, a movable container collecting online data from observatories around the world in form of sonified spectrograms transformed in art installations and decided to travel around Europe and even beyond. This is to say that IGO is a relevant actor in the European research area and beyond. As you can see from this slide, the partners of the projects we coordinate are located in South and North America, but also in Australia, as in the case of the Cost Action G2Net. Since my time is almost up, I just want to tell you that if you want to know more about our projects, I suggest you to visit our webpage or our social network channels. Or, of course, if you have any questions, you can also contact me via email. Thank you.
Thank you very much for that very brisk tour of an awful lot of work. So I do encourage everyone to have a look at everything that's going on at EGO. Our final speaker covers an important part of the project, which is the use of citizen science in formal and informal education. So I'm delighted to introduce Emmanuel Chandiakis, who's going to talk to us about that aspect of the program. So over to you, Emmanuel.
Thank you very much. It is wonderful to be here with all of you. Okay, so together we are going to discuss about gravitational waves and citizen science for education. So let me go a little bit back. We have all seen with the Nobel 2020 or previous Nobel Prizes that we have game-changing discoveries in physics with great media coverage. Okay, and the one of them about 2017 is the one actually that we are discussing today. And also these discoveries have an unprecedented impact in humankind, both in terms of knowledge and also in terms of spin-off applications. Okay, for example, the World Wide Web was discovered at CERN. Okay. However, if you browse the web, okay, and do it if you like, I challenge you to do that, and go, for example, let's say, what NASA is hiding from the world, you will see more than 7 million views here, or what they are hiding from us at CERN, more than 6 million views. And of course, we have the flat Earth believers who also have more than 1 million views in their videos. And this goes beyond hard science, okay? Also, if you investigate school curricula, you will see that 21st century physics is not systematically integrated in the K-12 formal education curricula, okay? And teachers mainly do not really feel confident to address students' questions regarding these developments, okay? So actually what we see is that we have a gap that exists between frontier research in physics and society, and in particular education. So to address this gap, Rainforce is proposing to utilize citizen science, let's say, as the glue between large research infrastructures in frontier physics, such as Virgo here, and school education. And to do that, you know, this is a win-win deal. First of all, we go beyond outreach. We are having people actually interact. We have people actually contribute to science. And for school education, large research infrastructures, as you saw from Massimiliano's presentation before, offer authentic research experience for students. They can help increase relevance and meaning of school science, and they can support the increase of student science literacy. And on the other hand, students and schools overall can contribute actually to the production of new knowledge or support the optimization of detectors such as Virgo, okay, because glitch hunting is actually this. Okay, and finally, they can act as multipliers to raise awareness for the work of such pioneering research infrastructures. So if we go and focus on the students, how do we envision them? We envision students as people who contribute in the optimization of research infrastructures and become actually partners with even a minor role in the research enterprise. We envision them to increase their sense of meaning in school education and, of course, their content knowledge. And finally, we hope that with this approach, we will increase their science motivation. Maybe some of them will want to join this endeavor from a professional standpoint. However, in order to do that, to achieve these goals, there are challenges we need to overcome. The first thing is that we need to introduce new topics beyond the school curricula. As we have seen, gravitational waves is not in the school curricula, not even special relativity or aspects of general relativity are there. We need now to balance the scientific goals of our citizen science projects and the learning outcomes we need to achieve with our students. The third challenge is that there is a big lack of teacher training and support, and thus teachers need to be supported in order to help us reach out to students. And finally, it is the classroom reality that we face, which is mainly the curriculum pressure and lack of classroom time. So in order to tackle these challenges, we have adopted a participatory design, which actually focuses on the following aspects. The first one is the design of a pedagogical framework, let's say an approach, a methodology, which we can follow in order to introduce these topics to schools. And this must be connected with rich educational resources, which we are developing right now to support this work. After that, we need teachers as partners with us. So we do teacher training and vision building. We support teachers to practice in real school environments, and then they come back to us and we reflect together on their practice, incorporate their feedback, and let's say improve our demonstrators. So this is actually all in a nutshell what you see. An example of our approach can be seen here, which is a gravitational wave noise hunting for schools. So this is a new topic, something that students have never heard about before. So we need to orient them, and then we need to guide them to generate their own hypothesis. With them, we need to plan our investigation regarding glitch hunting in this case, and do the analysis. And finally, one of the most important parts, the communication with scientists and with peers. So in the orientation phase, we introduce gravitational wave astronomy and detection methodology, okay, using, for example, simple setups or doing virtual and remote visits to research centers. Okay, this is something we did in the summer. Next, we have the hypothesis generation and design, and you need to bear in mind that since these topics are outside the realm of school science, we need to create bridging analogies. And as Massimiliano said before, if we imagine our gravitational wave detector as a near, then we can easily understand that as the ear's sensitivity is, let's say, downgraded when we have a noisy environment, the same goes about the gravitational wave detector. In order to plan now student, so we are discussing about formal education environments here, we need to explain specific topics to our students and also have them interact with them. Okay, so we need to explain signal and noise characteristics, to have them, let's say, play and identify sources of noise and how discuss how these affect detector sensitivity. We need to introduce them to the tools to identify noise patterns. So a spectrogram, as we saw before, is not something obvious for a 15-year-old student. We need to guide them through it in order to understand it. And finally, we need to describe the challenge. For example, here you see from an educational app created by Laser Labs, here the noise of a gravitational wave detector and the factors that influence it. We have, for example, noise patterns coming from earthquakes, okay? And we also have noise coming from the wind blowing. But finally, to us here, we need to understand transient sources of noise, which are the glitches here, okay? So as we do that, now we proceed into the investigation. So actually, this is the hands-on work of the students. Here, we use educational data sets to train students before initiating the project, and then we proceed to do the classification of data as Massimiliano presented perfectly before. Finally, we have the communication part in which using Zooniverse's great talk platform, students can discuss with their peers and with research scientists all over the world. So we implemented this and did a visionary workshop with teachers in the summer about gravitational wave noise hunting. Okay, and you can find the details in the presentation. And what the teachers participating said was that even though the topics discussed might not be really relevant to students' life, they believe that they will increase students' sense of meaning and learning in science courses. Of course, they identify the challenges to overcome, and most of them come from the school reality, lack of time, curriculum pressure, and others. And also, they believe that critical thinking and cooperation are learning outcomes that would be desired for their students. So what are our future steps? As Professor Casanueva said before, we're launching the Rainforest projects, okay, and we are initiating a series of 2-year-long participatory engagement activities with a great focus on students as well, Okay, and we are looking forward to working with you. Thank you very much.
Thank you very much. That's been a whirlwind tour in an hour and 20 minutes of sonification, citizen science, gravitational wave physics, detector technology, and last but definitely not least, citizen science for education. So thank you again, everybody, for joining us. We do have to end shortly looking at the time, but I'm going to take one question which has been sitting there for a while. So it's a question from Marcelo Manzarella, and maybe Massimiliano, this is for you. The question is really whether there'll be some system to show the results of the gravitational wave citizen science project. Will people be able to see the input that's been provided and what the results of the project are? So if you're there, Massimiliano, can you talk about that just for a second?
I could also reply to that.
Go for it, Stavros. Yeah, please.
Because I think our main goal, I mean, as we did in the past, we will be doing very often what we call hangouts, where we will all together be discussing, first of all, the results, the news. I mean, there will be a part where we will be talking all the new stuff that happened with gravitational waves independently of our program, and then we would all discuss our work together. I mean, I can say I was back in Paris a few years ago, and there was not exactly a citizen science. It was a MOOC, a massive online course, and we had the chance, for instance, to participate in the launch of LISA Pathfinder, which was a gravitational waves in space. We discussed during the launch with the people that made it happen, things like that. It will not be simply, you know, participating, finishing. It will, we certainly, and probably it's our fault that we did not stress it enough. Every month or 2 months, there would be meetings of the people working on the subject that where we will exchange, because we consider it a two-way process, and we want to learn from you also better ways to do things, and then probably also make suggestions, and then iterate again and again. So it will not be a silent process. It certainly will be a lot of back and forth.
Excellent. That's good. That's good to hear. I think that's always the mark of a good citizen science project. So thank you again, everybody, for joining us and listening. Let me remind you that if you want to keep in touch with the project, especially as we go forward with the other demonstrators, then you can follow us on Twitter. We're Reinforce EU, or you can go to the Reinforce webpage, which is reinforceeu.eu. Those links are in the chat for you to follow. Thank you again for joining us. Thank you to all of our speakers, and we hope to talk to you all again soon. Thanks a lot.
Chris, thanks, Chris, a lot from everybody.
Thank you all.
Thank you. Bye-bye.
Bye-bye.
Bye.
Ciao.
Ciao.
Bye-bye.
Bye. Bye, Massimiliano.
Good.